I'm excited to be talking to you about some work with the TROPOMI satellite sensor. It sounds like you're more on the experimental side, so I'm always happy to interface with people doing actual ground measurements. Most of my career has been working at the interface between modeling, data analysis, and real, ground measurements, that are mostly urban air quality. As you've here we go. As you've seen, I think from some of the past seminars, there's an explosion in new satellites for measuring methane. This is a slide I got from Daniel Jacobs' review paper. I should say 2022, sorry. And so we see these area flux mappers, so satellites that are able to cover entire areas. And especially the main workhorse of the past has been GOSAT. And now we have TROPOMI, which is the one I'll be mentioning today. And then MethaneSat is coming up soon. So people are excited about that. It'll be launched in next January, hopefully. On the point source images, these are satellites that target sort of individual areas, and especially GHGSat, this Canadian company, has several of those in space, and they're building a constellation and are getting very high resolution of direct methane plumes from specific places, which is probably would be of great interest to many of you. So what I'm going to talk about today is the results from TROPOMI, which is from the European Space Agency on Sentinel-5P satellite. It's been in orbit since October 2017. It's a polar orbiting satellite, so the Earth is like this, it's kind of orbiting like this, and it goes over our heads in, actually for me about now, and for California in about 2 hours time, every day around a little afternoon. It was designed mainly as an air quality satellite. So it measures NO2, we have formaldehyde, ozone, carbon monoxide, and then what's of interest here for today is methane. I have to tell you, when I first started out, I was heavily involved in the Mexico City field campaign in Milagro, and we were interested in NMHC, non-methane hydrocarbon, and just viewed methane as a nuisance for our air quality study because it's not very reactive, and so we didn't want it to contaminate our measurements of very reactive hydrocarbons. So it's interesting to see how things shift and interest shifts in science, and so instruments shift along with that. So before I get going with the methane, maybe just show you a little bit on nitrogen dioxide, which is easier to see from space because you can see it in the ultraviolet, which is a better place to look for things. And so we have nice retrievals. So here's an example from a published paper just recently, TROPOMI NO2 vertical column densities. So the satellite measures the entire column between the ground and itself. And we see this over Houston. And so you can see clearly the ship channel that has been much discussed by anybody in air quality in Houston. You can also vaguely see these point sources here. This is a big refinery, and there's a refinery and power plant here. There's a big coal-fired power plant here. And you can just about guess the highways from the TROPOMI NO2 column if you squint enough. So there's a new method called flux divergence, where we combine the winds with these maps to get a high resolution estimate of the sources. And so when you do a flux divergence over Houston, you can really see it picks out some of these hotspots. Now this coal-fired power plant really shows up here, the ship channel really shows up. And the highways actually also show up a little better. I'll go back. It takes a while to make these pictures, so we're always fond of going back and forth just so people could see the difference. So we're really getting to that point where the satellite is able to identify individual sources for NO2, which is good. And NO2 is pretty well understood compared to methane, and yet there's still a lot of work to be done. This is the same method looking over Dhaka in Bangladesh, just a little north of Bangkok. You can see the columns over here on the top left, and it kind of shows this elongated egg shape here over Dhaka. When we do the flux divergence, we're able to see individual areas. And so then what we do is we match two-dimensional Gaussian maps to these hotspots and estimate the emissions that way. And that's what these green dots over here on the lower left are, estimates of emissions for these different areas. And it's like, well, great, we now have our estimate of emissions for DACA. NOx is pretty well understood. So if we compare it to an official emission inventory, we should get a good comparison. And so on the lower right, you have the EDGAR emission inventory, one of the main global emission inventories from the European Research Council. And you see there's good agreement actually for the industrial sources here in Narayanganj. This big green dot is kind of the combination of the purple emissions down here. But there's actually very poor match in other places. These lighter blue dots are from the energy industry, power plants. EDGAR thinks there's a lot of NOx coming out of those. And the satellite really hardly sees any. You can see in the top right, just a faint blur. On the other hand, EDGAR doesn't have much by way of urban emissions over DACA. The light blue is mostly power plants, but and it doesn't have any here to the north of DACA. That these are light manufacturing centers. So we're getting to that point where TROPOMI can be used to really improve the emissions inventories and guide the development. And so the good news is there's a lot of improvements to be made. So I'll move now to methane. And again, I'm assuming people are fairly familiar with this. Methane is harder to measure because it doesn't have a signature in the ultraviolet. It's in the infrared. So we go into the shortwave infrared, the near infrared, and there's a lot of noise in the infrared. So there's correspondingly more noise in the data. The other problem with methane is that the background is so high, it's around nearly 2000 ppb. And so if you're looking for an enhancement that's like CO2, if you're looking for an enhancement in CO2, you better have a very, very precise measurement. Whereas for NO2, the background is mostly zero. And so it's all gravy. Any detection you make, it's good. It's an enhancement. So here you have the average map for 2019 from Alba Lorente at SRON doing these retrievals of TROPOMI. And you can see these enhancements over tropical ecosystems, over agricultural areas, and then and here, especially in Asia, a lot of rice paddies, a lot of agricultural emissions. So that's what we're kind of starting with for today. If you zoom in just over the US, you have Jos de Gauw have published a paper looking. So on the bottom, we have NOx, nitrogen oxides. They're mostly emitted by traffic by power plants. So that's what I showed at the beginning of this talk. I had showed a zoom over Houston here, this tiny area. This is pretty well understood. It's nice and clean. Everybody's happy. You look at methane and it's a lot noisier and there's still a lot more uncertainty. You can definitely see oil and gas here in West Texas. You can see agricultural areas, here, the Mississippi River Valley, wetland in Florida, agriculture in the Central Valley. Actually, there's also oil and gas in the Central Valley, so California. But you can see it's a noisier picture for methane than for NOx. The next kind of jump then in scale at the local scale, and this I pulled from Johan Masaka's paper on landfill emissions. This is with GHG sets. The GHG set, you kind of work with a company and they will target your source for you and give you some scenes of your source. And you can see on the top left here, a nice methane plume from this massive landfill that's in the north of Buenos Aires. And I'll come back to that later with the TROPOMI results. But this will see, you can actually kind of see structure in the plume and, so if you have a specific source, this is what you need to get to in a way that the satellite cannot see. So what I'm presenting today is in a sense halfway between the previous two at the urban scale. So we're closer in than the regional, but not yet at the GHG set point source level. And because I was working on DACA for air quality reasons, I thought, well, let's just pull out the TROPOMI methane data and see what's there. And what you find is this nice urban methane enhancement. This big hotspot that is over the magenta line is the contours of high population density, which, by the way, astronomical in Dhaka. It's the most densely populated city in the world, I think. very, very densely populated. So, but we've got a, for an average of around 2000 ppb, we've got an enhancement of 20 ppb. So it's like a 1% enhancement. So if we compare that to the emission inventory, we're like, well, we should be able to see some sort of comparison. And we see something that's even worse than NOx. The emission inventory in EDGAR is mostly FFL, here, fossil fuel facilities. So I combined everything to do with fossil fuels, these 4 orange spots. This one is in the city. So, I mean, it's in my methane hotspot, but the other 3 are not. I mean, maybe some of this is caused by this, but you can see there is no clear match between the 2. Most of the methane down here, this big circle here, the blue circle, is the sum of all the little circles, the little empty circles here. And that's mostly agricultural. So we have mostly methane from rice paddies. But you can see from the picture that that's not what we're getting. We're getting a clear urban enhancement that is not a general agricultural enhancement. So I thought, well, this is interesting. Maybe you should look at a few more cities while I'm at it. Why not? And so this is a collection of cities, kind of chosen for different reasons here, but you could see Buenos Aires that we mentioned. The white diamond here is the one that had the big landfill with the GHG methane plume. But in fact, in TROPOMI, the methane enhancement is over the whole urban area. In Lahore and Delhi, we have methane enhancements. They've sort of extend towards the east, and that's mainly because of the dominant wind patterns. You have to keep in mind TROPOMI only sees clear skies. So for cities that have very clear dry and wet seasons, you'll be mostly looking at the dry season, which means you'll mostly have the dry season wind pattern. So that, but you're getting mostly sort of methane from the urban area kind of being transported to the east. Houston is kind of noisy, and this is what we get a lot of. So, but it's still elevated over the urban area, and not so much. I mean, Houston has these landfills all over the place, but it doesn't really match. Sometimes it matches, but it could be by chance or not. We don't know. Lagos in Nigeria, similar thing. There are landfills, but the overall enhancement matches more with the urban area. In contrast, Madrid has clear hotspots that are tied to the landfill. So this is nice because it tells us, well, if it were linked to landfill, this is what we would see. And then we can go to the other cities and say, well, but is that what we see, yes or no? So this is kind of a zoom on 6 cities. I did this for as many cities as I could do and ended up with my summary figure here. There, in the end, 61 cities for which I found a clear enhancement. So if I start from the bottom of the legend here, the red dots are places where there were no retrieval. There wasn't enough data to really say anything. Most of those is because in the tropics, it's too much cloudiness, so that rules out the data. Some of them are in the mountains, that rules out the data. Some of them are in deserts, so too much reflectivity off the sand, that messes up your retrieval. Some of them, like I was kind of hopeful for here, Seattle and Portland, too much water on a too complicated coastline. Filtering out coastline pixels turned out to be a monumental task, not to say a big nightmare. So that's the red spot, 35 with no retrieval. Blue spots, there were retrieval, but there was no sort of detected clear enhancement over the urban area. And these are kind of mixed out throughout. The black squares are places with regional emissions. So here we have Yangon and Bangkok. I'm glad we have a Bangkok representative here. These are places where there is an enhancement, but it's not just the urban area, it's the whole region. And so we can't distinguish whether it's urban methane or whether it's agricultural methane, because it's so I put those in for completion because I just wanted to be upfront about everything I did. Xi'an is the same in China. The enhancement is that whole valley with lots of agriculture in it. But we're still left with these big dots. The size of the dots is the size of the emissions. The largest emissions here was in Dhaka. So it's kind of fortuitous that I started off with the clearest city. I might have gotten discouraged, if I'd started off with, I don't know, Khartoum or something. 1,400 kilotons per year. These are very large values. The color of the dot is kilograms of methane per person per year. So in the Asian cities, that's actually not that high because the populations are so high, it's so densely populated. So in Dhaka, we're in the 50 kilograms per person per year of methane. The big baddie in this is America. Hey, we have, our emissions are not the biggest, but we have the darkest spots there. I think Baltimore gets the prize at 372 kilograms of methane per person per year, just estimated from TROPOMI and from a database, a global database of population. Not so much emissions from Europe, they're fairly clean, and not that many hotspots detectable in Africa. And Latin America has all these retrieval problems. So I thought, well, this is good. We'll do this, and we'll compare it with EDGAR, and we'll see, maybe there wasn't a good map, a good comparison sort of spatially at the fine level, but maybe overall there is kind of some correlation. And this is the scatter plot on the bottom of the EDGAR total methane emissions for each city, and along the y-axis, the TROPOMI methane emissions. And you can see here R squared 0.02, R squared 0.01. No correlation at all between the two. So that was kind of discouraging. I then did these by sector for all the different sectors in EDGAR, and it was the same result. So we're kind of scratching our heads, thinking, well, how are we going to move forward on this? And we were fortunate to come across these Dutch guys, Edward Jones and colleagues, have a big database, and maybe people who are working in water, wastewater, must know this much better than I do, but they've made this database 10 kilometer, roughly 5 arc minute spatial resolution, the whole world, how much wastewater was produced, how much wastewater is collected, how much is treated, untreated, reused, everything. So that looks promising. We know methane comes from wastewater. So we totaled up our wastewater for each, and you can see actually in America, you can see these little red spots if you squint enough. Lots of squinting here. Untreated wastewater from cities. There actually are not as many in Europe, except in Belgium, which is where I'm from. I don't know what that's about. All these things you find out that you never knew when you look at the data. So I did this, and that's the sources of those. I mean, we will kind of know, this is methane from an open channel sewage. I think I was in Dhaka in March, and you could see kind of sewage flowing along the sidewalk in little gullies like this, and all this methane bubbling up. In America, we tend not to see that as much, but we do have all our old cities have combined sewer overflow. So in this diagram, normally our sewage goes to the sewage plant, but when there's a big storm, the storm goes to the same pipe, it mixes up and it's released to the environment. So we have these different possible causes of methane. And when I plotted, then this is a different way. I plotted the scatter plot as a box plot to be clearer. You have methane emissions per person here for the high income countries, so North America, Europe, and some of the wealthy countries in Asia. And I classify them by the amount of untreated wastewater that they release per person. So cities with 0 untreated wastewater, these actually are mostly European cities, have the lowest emissions. And then low, medium, and high, we have a nice straight correlation here. Cities with a lot of untreated wastewater emit the most methane. And we see this for Asia as well, from low to medium to high. We don't have enough cities for Africa and Latin America, so I just put all the cities together, Africa and Latin America there, and yeah. So this is pretty promising, and it's actually a remarkably robust relationship, whichever way you kind of cut the data, that relationship was still there between and it was kind of with all wastewater, but it was more specifically untreated wastewater. If we zoom in on the US, there's kind of an interesting case study here with Milwaukee and Minneapolis. You can see Milwaukee has as many as that as Baltimore in terms of per capita emissions, in the 300 kilograms of methane per person per year. Whereas Minneapolis doesn't have any signature. And so this is where I'm coming in as a non-expert on the outside, but after the paper was published, one of my co-authors was talking to somebody who says, oh yeah, actually Minneapolis has made this massive effort at reducing their sewer overflow events, sort of more than other comparable cities. So here are two cities that should be the same, but in fact, where you see, possibly this is a hypothesis, but that sort of improved treatment of water would reduce your emissions. So some of the Northeast cities here have a fair amount of methane, and then in Texas too. So that when you put all this together, you get three main conclusions here shown in this one table. The first conclusion is that urban methane emissions are underestimated in the EDGAR emission inventory by a factor of 3 or 4. If we look here at the top line, 61 urban areas in the data set. With TROPOMI, I estimate around 25,000 tons per year. 25,000 kilotons per year, 25 million tons per year for the whole group. Whereas in EDGAR, there's only 6,700 kilotons per year. So that's a big difference. And that difference goes for both the cities with low wastewater and with high rates of untreated wastewater. In TROPOMI, there's a big difference in emissions between those, but in EDGAR, there's no difference at all between those different cities. Conclusion number 2 from this is if we took those 61 cities, if we took the 33 cities that emit the most and reduce them to the average level of the lower emitting cities of the bottom 28, whatever it is, here, you would have a 2% methane reduction globally, just from these 33 cities, which, that's for 33 cities, that's sizable. And that's from 186 million people. If we were to reduce all 61 cities to the lowest possible rate, this 10 kilogram of methane per person per year, this is the value for Seoul in South Korea, then we would have a 6% reduction in methane worldwide, sort of estimated. So just those 61 cities. And then the third conclusion then at the bottom says, well, what if, this is just the 61 cities that TROPOMI can see. What if we assumed, roughly speaking, that all urban areas suffer from the same problem? What would their emissions be? And if they all, there's 385 cities with more than 2 million inhabitants, half of which are in China. If we have them all emit sort of median low level here, 40 kilograms per person per year, that would amount to 60,000 kilotons per year of methane. That would be 22% of the global inventory. So a lot of methane. And if we were to reduce that, by 50%, then we would reduce our emissions by 50%. So we would have only 11% of the global fraction. And then we could, if we reduced it all to Seoul, then we would reduce that number further to 20,000 kilotons per year. Okay. So overall, the potential would be to reduce methane emissions by 10 to 15% overall. The nice thing with this is that, the clear co-benefits, that this is something we should be doing anyway, because releasing untreated wastewater to the environment is a bad thing. And so if we could show the clear co-benefits between the, different things that we should both, we should be doing all these different things, and all the more so because the overlap of the co-benefits. So that was the main thrust of the paper. The paper's online, at Environmental Research Letters, and I'd be happy to answer any questions you may have.